Early 2025 saw an exponential explosion of developer interest in the Model Context Protocol, or MCP. Anthropic actually released the protocol quietly in late 2024, but despite the hype, MCP adds 0 new functional capabilities to large language models. If you need an AI to read a database or trigger a script, you can achieve identical results using standard OpenAI function calling. MCP is a structural decoupling. It acts as the HTTP of AI tool access. Compare the legacy approach on the left, building bespoke API wrappers for every individual service, with a single unified protocol layer connecting to diverse data silos on the right. This intermediate layer standardizes the interface schema. Whether you are pulling a PDF or querying a SQL database, the format presented to the AI is identical. This unifies connections to platforms like Slack and also GitHub into a single standard. The problem is, current tutorials trap developers into thinking MCP is only for local desktop environments. Deploying MCP at scale requires abandoning these local node locks and embracing remote transport architecture. In the legacy method of building AI applications, a Python app's core LLM call is tightly coupled with custom integration logic. Maintaining these hard-coded, bespoke wrappers creates significant technical debt as integrations grow. The MCP strategy breaks the monolith into 3 distinct nodes. The host is your primary application where core LLM orchestration lives. The client is the protocol manager handling the connection standard. And the server is an isolated container holding specific tools, resources, and prompts. Because of this separation, the host application no longer needs to know how a tool executes, only that it is available. Setting this up is straightforward using the Python SDK for MCP, which uses a syntax similar to FastAPI. Decorating a Python function with the mcp.tool decorator automatically serializes that code into a standardized JSON schema. Most quick start tutorials connect client and server using standard input I/O, or stdio. This method locks both nodes to the same physical machine, preventing scaling. Spinning up a dedicated server just to run a local script is an over-engineered bottleneck. Relying on standard I/O for a standalone backend creates friction that obscures MCP's capability for distributed scaling. Resolving this bottleneck requires shifting the transport layer to server-sent events, or SSE. Packaging the MCP server into a Docker container allows you to physically decouple the tool logic from the local environment. This changes the connection pipeline from a local file call to bidirectional communication over HTTP. Exposing this container via port routing makes the tool logic completely network agnostic. Now, multiple distinct host applications, from corporate desktop tools to custom web backends, can connect to the same remote container simultaneously. For example, enterprise teams can route all Google Workspace connections through a centralized server rather than configuring individual app integrations. This HTTP shift transforms the server into a universally accessible API for any authorized AI agent. Transitioning to Dockerized SSE elevates MCP from a local script manager into mature, distributed enterprise AI infrastructure. We can prove the host application is fully decoupled by tracing the exact sequence of a remote tool execution. Step 1. The client pings the remote MCP server and requests the available tool schema. Step 2. The client passes this schema and the user's prompt directly to the LLM. Step 3. The LLM analyzes the prompt and returns a specific tool call command. Step 4. The host application does not execute any code. The client intercepts the tool call and routes the argument payload to the remote server. Step 5. The remote server executes the raw Python function and passes the localized data result back to the client. Step 6. The client hands the final data back to the LLM for final synthesis. Because the execution domain is physically separated, the host application remains secure, lightweight, and agnostic to the underlying tool logic. In this optimized architecture, the central host application operates as a router with 0 hard-coded logic. If you have an existing AI app that is perfectly functional, there is no technical reason to rip out your current function calling logic. However, new applications that require reusable tool infrastructure shared across multiple enterprise teams benefit from this centralized model. Standardizing tool execution via MCP and SSE brings distributed engineering principles to the AI backend.